Ohayou gozaimasu. Watashi no name wa Desirée Plata des. Today, I'm going to talk to you about one of the most important challenges of our time, having chemical and material innovation while also accounting for environmental, social, and economic sustainability for a more prosperous planet and society. This is an artist's rendering of the Big Bang. Within the first 3 minutes of the creation of our universe, we had all of the elemental building blocks that we would be able to draw on to use materials and chemistries that we have today. Now here I'm showing the most stable elements in black. Over 3,000 nuclides exist and 3,000 more are predicted to exist in the near future. Now, the tools of chemistry and material science allow us to manipulate this finite set of elements to gain access to new materials and new properties that we haven't been able to access before. Now, the trick, of course, is being able to do this without harming the environment or the Earth system. We are witnessing planetary change. Here's an image from the Eastern Hemisphere in New Guinea, where in the 1980s, you could see ice cover on the mountaintops. But today, you see very little ice cover in that same region. Interestingly enough, on the left-hand side of this image in the purplish swirls, you see a strip mine, a large-scale strip mine where we've extracted mineral resources from the Earth's surface. And this isn't just an image taken on a faraway island. There are images like this all over the planet. So no matter where you call home, you can witness in the impacts of global climate change. Now, ironically, in order to solve these problems, we need materials innovation. We need new chemistries. We need innovation, but we need to do it in a different way. Now, the problem with status quo material innovation, I'll walk you through. What I'm showing on the y-axis is the investment in a technology versus the relative profit as a function of time. Now, the point of inception of an idea is all the way on the left-hand side of this image. And as we move to the right, we see that we invest in proof of concept. We as engineering professors and science professors like to teach about optimization for performance and cost, and performance and cost. And if you work in industry, these are some of your daily constraints. And once we get past this proof of concept phase, we invest heavily in industrialization of our technologies. And these investments tend to be measured in orders of millions of dollars. So if there's a mistake that occurs here, it's going to be propagated, and chances are that it's going to be difficult to fix it. Now, as we begin to sell and distribute our products, accumulation of materials, whether they're byproducts or the primary material themselves, starts to occur in the environment. And this can sometimes lead to a malignant environmental or public health impact. Now, on the order of about 10 to 40 years, this might lead to a voluntary product ban and what I call the 4 R's of doom: reparations, remediations, public relations, and reinvestment in a technology. And what we tend to do in American society is change one bond to get us to a new technology that does the same thing, but circumvents regulation, or perhaps helps us believe that we're not going to cause a problem for our fellow citizen or for ecological systems. And it turns out that that's not good enough. So I'm here to argue today that most of you sitting in the room got into this business to build technologies that would last more than 10 to 20 to 30 or 40 years, and much longer, in fact. And in order to do that well, we need to account for sustainable design early in the optimization process. So what I mean by this is that once we get just past proof of concept for some of our ideation, we want to include those traditional performance and cost metrics. Those need to be there, but we also want to include environmental metrics as well. Now, of course, this takes a little more time initially, but if we do our job right, we should be able to bring this product to market with only a slight delay, but at a lower cost. And this leads to kind of the dream: relatively low accumulation of a material in the environment and sustained profits for all time. We're kind of witnessing this happen with the silicon chip. We didn't make our semiconductors out of gallium on purpose. We had abundant silica. We thought we could do it safely. So we can make those types of choices with our material innovations today to ensure a more sustainable planet and society. Now, some noteworthy concerns about this approach are the time for innovation, the relative cost associated with that early investment, and making sure that the functional performance of the material or chemical process is maintained or perhaps improved. Now, I want to pause here for a second to talk about the word sustainability. I feel like when we say sustainability, everyone looks at each other and nods and smiles as if we know what we're talking about. But it's actually a bit like this old story in Western culture called The Emperor's New Clothes. Now, the story of the Emperor's New Clothes was one that basically said that the emperor was told he had nice new clothes, and yes, he looks beautiful. And because person A said the clothes were beautiful, person B started to say, yes, of course, the clothes are beautiful. Meanwhile, the emperor's marching around in his underwear, but everybody in society was being told to say that it looked really nice and chic and novel and new. And so that should be applauded. But really, everyone was thinking, wow, this is really not good. I don't know what I should be looking at here. And so this is kind of what's going on with sustainability right now. Every company in the world is talking about sustainability and thinking about how they should do it. And that's a great and good thing. But we don't necessarily know what we're designing for. I'm here to tell you today that there are existing environmental criteria that we can use for environmental optimization. Now, sustainability has a definition, it turns out. The United Nations met in the late 80s to say that sustainability really means meeting the needs of present society without compromising the ability of future generations to meet their own needs. And this definition of sustainability has since adopted really three pillars: social, environmental, and economics, or people, prosperity, and the planet. So we tend to think about sustainability using these three pillars of sustainability, and we can assign rigorous quantitative metrics around each of these. I'm going to tell you an example today that relies on carbon nanotubes as a case study. Carbon nanotubes were famously first described in Japan in 1991, and you can see the growth in the commercial applications of carbon nanotubes ever since. We produce these by the thousands of metric tons per year. This is not a niche market anymore, but something that has a meaningful impact in society. Now, unfortunately, the way that we make nanotubes is one of the most wasteful industrial processes of all time. Now, there's a lot going on in this figure. I want to draw your attention to the highlighted column of the E factor. That's the waste to product ratio. So the higher the E factor, the more waste you have relative to the amount of product that you are trying to sell. Now, the industries I'm highlighting include oil refining, bulk chemicals, fine chemicals, pharmaceuticals, and carbon nanotubes. And what you also notice on this image are the years in development. And the older a technology gets, the better the E factor tends to be, the more optimization occurs. Now, unfortunately, we tend to innovate so quickly these days that we never drive down E factors very much anymore. So even for pharmaceuticals and fine chemical processing, we tend to have very high waste to product ratios. This is something that we need to work on. In the oil industry, of course, we sell every little fraction. We don't have asphalt on our roads because asphalt's a particularly good substance. We have asphalt because we need to sell a lot of it. Okay, so when it comes to carbon nanotubes, it turns out that only about 1 in 10 on your best day, or 1 in 10,000 on your worst day, of the carbon atoms coming into the system are actually becoming a carbon nanotube, and the rest are going out the tailpipe. And that's exactly what I asked early on in my doctoral dissertation work. Of all the carbon atoms coming into a carbon nanotube reactor, what are they forming? What are they becoming before they exit the tailpipe? And what we saw is that a broad suite of volatile organic compounds, those are the cartoons shown on the left, and polycyclic aromatic hydrocarbons, the structures shown on the right, were being formed. Now, we had to develop some analytical methods to be able to see all of this with order of magnitude improved sensitivities. But what I'm showing you is that as a function of temperature, which was important to achieve carbon nanotube growth, certain chemical species increased while others sort of hovered around similar values. Now, volatile organic compounds are the compounds that contribute to smog formation in the upper atmosphere, whereas polycyclic aromatic hydrocarbons are the compounds that are responsible for the color in a cigarette smoker's fingertips. They're the compounds that will eventually give you cancer if you are a smoker. Now, what we noticed is that as temperature increased, so did the concentration of some of these chemicals. We hypothesized that some of them were just there as byproducts, whereas others might be critically important for the reaction itself. Emissions, it turns out, in that environmental assessment perspective, are really just reaction products. They gave us a lens into what was going on to form the nanotubes in the first place. So what we hypothesized was that really it was the triply bonded species, things called alkynes that have a C triple bond C moiety, are the things that can bind best to the metallic centers that are responsible for the catalytic processes occurring in these reactors. We think that this occurs due to something called pi back bonding. Empty d orbitals on, say, iron as a catalyst are able to interact with the filled pi orbitals on an alkyne, a triply bonded species, and facilitating that interaction can allow for long range order polymerization reactions to occur. So we tested that using a cold delivery approach of these different alkynes, and it turns out that that hypothesis was supported. Now, we asked ourselves, is this an opportunity to actually fine tune, control the molecular atomic scale structure of the carbon nanotubes? Now, if we believe that acetylene and methylacetylene and vinyl acetylene are all capable of growing carbon nanotubes, we might hypothesize that acetylene should give a fairly straight tubular structure where those rings are able to close completely, forming nice hexagon patterns. We might hypothesize that methylacetylene, which has a CH3 group on the end that's sp3 bonded, might actually frustrate the ring closure and not be able to participate in a polymerization reaction. That might give a very tortuous structure. Vinyl acetylene, which has a filled pi orbital on the end, might actually be able to participate partially in these polymerization reactions and bond with those metal centers like on an iron catalyst. That might give a structure somewhere in between. So there's a cartoon representation of our hypothesis, and here's what it looked like under transmission electron microscopy. And now, depending on what you've put in your coffee this morning, you might say, yes, this is supported. We see very straight structures in the acetylene-fed growth, more tortuous or wavy structures in the methylacetylene-derived carbon nanotube forests, and something in between for the final acetylene forests. Now, we wanted to be more quantitative and rigorous about this assessment, and so we turned to a technique called X-ray scattering. So using small and wide angle X-ray scattering, we are able to see molecular scale features of the structure. So X-ray and a beam of X-rays can be introduced or impinged on a well-aligned carbon nanotube forest, and the degree of scattering of those X-rays is inversely proportional to the feature size that you're interrogating. So something we call Q, the scattering vector, can report on the molecular and atomic scale features within a carbon nanotube forest. So we can extract things like alignment, interwall spacing, and the molecular structure of the rings themselves. So what we saw here is that we did in fact observe independently tunable atomic scale features in these nanotube forests. And the features that we were able to observe were consistent with our hypotheses, these environmental emissions derived hypotheses. So looking at something called the Hermann's orientation factor, which is a measure of alignment, we found that the acetylene structures and the vinyl acetylene structures were indeed the most aligned, and both more significantly aligned than the methyl acetylene structures. The interwall spacing, on the other hand, the spacing that exists between concentric nanotubes, was tuned in the way that you would anticipate if those side groups were persisting. So acetylene has the smallest interwall spacing, whereas methylacetylene, where you have to accommodate a methyl group, has a slightly larger interwall spacing, and vinyl acetylene has a larger still interwall spacing. This is a remarkably conserved number in nature. The interlayer spacing of all graphitic materials occurring in nature is 0.34 nanometers. And we see that same measurement here with slight variations to accommodate those side groups. This was a really remarkable finding. The other thing that we were able to image in situ intact structures were the existence of the methyl groups themselves. So what I'm showing you here is an acetylene grown forest, a vinyl acetylene grown forest, and a methyl acetylene grown forest, and their respective drip lines for replicates. This is not just one sample, but many, many samples. And what you see is the emergence of an indication of the existence of methyl side groups in the carbon nanotube structure. This was really exciting. We also see things like persistent alkyne bonds in solids, which opens up a world of possibilities for manipulating the structures themselves and doing point-directed functionalization. So we asked the question, can all alkynes grow carbon nanotubes? Can anything with a triple bond carry its heteroatom cargo into the nanotube structure? Now I'll show you an example just with oxygenated alkynes. And the idea here is that maybe you could grow a nanotube from something like acetylene and then start growing that nanotube from something like propargyl alcohol, a triple bond with an alcohol group on the end, and then return to growing your nanotube structures with something like acetylene that has no functionality. This would allow you to deposit oxygen groups where you want them, and then maybe replace them with something else, whatever your desired chemistry might be. So when we looked at this and tried to interrogate it using attenuated total reflectance, Fourier transform infrared spectroscopy, we were able to actually see the persistence of those alcohol and carboxylic acid groups into the carbon nanotube structures. Now, the way that you read this is to look at the first three images, for the raw images for acetylene, then propargyl alcohol, and then propiolic acid beneath it. Now, I'm going to do something beneath this dark black line where I subtract the acetylene wiggle from the propargyl alcohol wiggle, and that's going to give you the red line right under the dark black line. And then I'm going to subtract that acetylene wiggle from the propiolic acid wiggle, and that's going to give me the blue line below it. I've marked the 0 point in a light black line around each of these. So anywhere where you see that red wiggle in the bottom part of your screen deviate from center, and so you can see white space, that's a place where there's a real molecular feature that persisted in the replicates in this experiment. And the same thing for the blue. And what we start to see is that there is oxygen functionality persisting in these nanotube structures exactly where you would expect. You see an alcohol stretch for the propiolic acid fed nanotube groups. You see a carbonyl stretch, especially in the nanotubes that are grown from this propiolic acid. This is really exciting. As a point of reference, you'll notice that most of the signals are red shifted. This is because they are in a tightly constrained nanotube forest. So we're able to image these in intact structures and see that these triple bonded alkynes are carrying their molecular cargo with them into these carbon nanotube polymers. It's really exciting. Now, the question, of course, becomes, can we leverage this new molecular understanding to try and improve sustainability metrics? We know we can get better control over the structures, but can we also do it at lower cost and with lower environmental footprint? Now, the idea that I'm trying to show here is that in industrial manufacture, when you want to get an oxygen group on a carbon nanotube, you might reflux it in hot acid for a long period of time, wash it, and then do some subsequent chemistry to try and get the groups that you want in the places that you want. It tends to be quite random, actually. We tend to only add oxygen groups where there are defects in the forest structure and not where we want them. The idea here is to actually just directly add the alkynes where you want them to be able to give you a molecular handle to be able to add other subsequent chemistries. So this is a very exciting advance. We think this is a new way to nanotube, and this is Eric Johnson, the student who was responsible for most of the work I just showed you. We're also able to see that we have a 50% lower energy consumption using this alkyne-assisted carbon nanotube growth. We are able to reduce the starting material requirements by an order of magnitude or more. And we have many orders of magnitude lower hazardous emissions. So those VOCs and polycyclic aromatic hydrocarbons that I showed you earlier can be next to eliminated in the effluent stream. And so this is gives you much better control over your process and also provides great environmental benefits. So you don't have to worry about your neighbors, the planet, or ecological systems that would be impacted. Now, the materials innovation that I've demonstrated here offers control over the alignment of a nanotube structure. Maybe you could use this to make a nanotube turn at a particular point in time. We can see the importance of this for interconnects potentially. And we could also think about delivering functional groups exactly where we want them in something we call point-directed functionalization, or even hybrid nanomaterials that we have yet to demonstrate that may even be yet unimagined. So what else can we do to inform sustainable materials design? I don't want to take up too much of your time with this because there's actually a large body of work in this space right now, but I do want to highlight a couple of different tools that are emerging that you would be able to use to help improve your own industrial processes and practices, hopefully not just for environment and societal benefit, but for an economic benefit as well. Now, the problem is that I mentioned this tends to take a little bit of time. The other problem is that we don't start environmental optimization or societal optimization for that matter until it's too late. I call this the environmental discovery gap. We typically see demonstrations of proof of concept of the applications of a new material or chemistry at least 20 years before we see assessment of environmental impacts. That's often when it's too late because we've already invested in the infrastructure to make, distribute, and process the materials that we are creating. So here I'm just showing an example for some nanomaterials like graphene, carbon nanotubes, nanotitania, and nanosilver. And what you notice is that the publication records spike in the 90s around the application space, but the environmental health and safety research doesn't come for another 20 years. That's something that we have to change. Here are 4 ideas to help us make those changes. The needs that emerge are that we need high throughput experimentation. We need to be able to make discoveries about environmental fate, toxicity, and environmental performance sooner so that it can inform design. We need better fundamental science. We shouldn't have to experiment on every single new chemistry we create. We should be able to know something about the structure and be able to predict where it will go in the environment, what its hazards might be. We call those structure property function or structure property hazard relationships. We also need coordinated data sets. If I'm making a discovery in my lab, I should be able to relate it to a discovery that's coming out of a lab in Japan without problem. We should be able to do this through autonomous literature searching. And I'm hoping that becomes a reality if we can publish our papers and our patents in the right way. There's also something to be said for trying to have interoperable patent data sets that also help an industry benefit from partners within the same industry who are trying to answer the same difficult questions without compromising intellectual property. The last thing, and this exists today, are something called material selection databases. Material selection databases allow you to do multi-parameter optimization, even for things like environment. Today, these mostly exist for impacts like CO2 and global warming potential and energy consumption, but may someday also include things like toxicity and implicit hazard or environmental fate. Now, to establish a high throughput workflow, we need to micronize our experimentation. We can't have an individual PhD student studying one chemical for 5 years and then telling us a little bit about the environmental fate. We have robots that can produce hundreds of new chemistries in a day at MIT. I should have the ability to anticipate the environmental fate of those new chemistries and test some of them on that same timescale. This is just an illustration of the type of thing that we're trying to develop, where we can perform environmental fate transformation reactions in high throughput and look at, say, the total production of organic matter from a polymeric solid like a plastic bead, and also know precisely what the composition of that organic matter is through things like liquid chromatography and gas chromatography with high resolution mass spectrometry. I'll show you an example of when we did that with 2 polymers in our laboratory. We found that there are many unique compounds that were formed from the weathering of these polymers and hundreds of transformations occurring. Now, these are just the transformations. This is not all dissolved organic matter that was formed, but we can look at the relative distribution between scission reactions when we're cutting things up and cross-linking reactions when materials are coming together. When we hear environmental fate, we tend to only think of degradation reactions, but we should remember that molecules can react to come together to form larger structures as well. That's how we get dissolved organic matter in the sea, of course. And we can also start to investigate more specifically what's going on in these individual reactions. So hoping this video will play for you momentarily. Now, what I'm showing you here is in the blue arrows, you're looking at cross-linking reactions. The red arrows are scission reactions, or where we're getting cuts in a molecular structure. The yellow features are features that are growing in size, and the blue features are features that are decreasing in size during the course of the experiment. So you're looking at kinetically resolved information. So now we can actually drill down on these molecular transformations and look specifically at what chemistries are changing. What is the mass to charge ratio of the parent and the daughter? How are they tied together? And does that make good logical sense from a chemical perspective? Now, the possibilities for this are vast. We can start to drill down on specific molecular transformations and ask about fundamental transformations that might be universal to all of that particular chemical functionality. That would allow us to predict the environmental fate of specific structures. Now, I mentioned structure property performance relationships and structure property hazard relationships. Now, there's a lot going on this image. But what I want to highlight is that something about the nanomaterial structure or a chemical structure is giving rise to the functional performance that you want as a designer. That same thing might also be giving rise to the hazard that you would observe in the environmental system. That could create a problem because it means that you might not be able to decouple your function from the hazard. But if you can pull apart the function and the hazard, if the same molecular property isn't driving both of those things, then you would be able to tune them independently. So again, if we have an overlap of our functional performance and the negative environmental impact, that's the case shown at the top of the screen on the right-hand side, then that would be something that would tell you you should pivot to a new chemistry here or a new material. Whereas if you look at the bottom of the screen, we see that the functional performance is actually optimized, or at the top of the chart, when you get a non-hazardous effect. And so that is a good thing because it means you can start to manipulate your chemistry such that you get the great functional performance you want while avoiding the implicit hazard to the environmental system. And the importance here, of course, is meant to drive a fundamental understanding that allows you to predict this type of thing as opposed to having to measure it for every single new chemistry we innovate. Now, in order to be able to do that, we need to have intercomparable data sets. The image that I'm showing you on the left-hand side was a manual data processing effort by a student of mine many years ago to try and look at what temperatures simply were needed when you made nanotubes from methane, ethylene, and acetylene, the most common precursors used to make carbon nanotubes. And what we found is that when you use methane, you have to operate at a higher temperature. That's what's being shown in the top left panel. But when you use acetylene, which is actually responsible for making the nanotube structures, it's the important precursor, you can operate at a much lower temperature, offering you some sort of environmental benefit if you know the right recipe to use, of course. Now, the aspiration here is that we should be able to not have my poor student go and read hundreds of journal articles by hand, but actually be able to machine read journal articles. In order to do that, we need to have standard keywords that would allow us to machine read articles or patents and be able to interpret the important process chemistry or the key innovation. We also need to know when the chemistry didn't work. That's something that we often don't report in scientific literature. And it's critically important to have those failure modes so that we can machine learn away from them. So this natural language processing has been greatly advanced by a colleague of mine named Professor Elsa Olivetti at MIT. I encourage you to look in to her work. The last innovation that I want to talk about is something called multi-parameter optimization. Now, this was an idea that was launched by Mike Ashby, who is famous for collating materials databases. And in his work, he tended to use these materials databases to help co-optimize things like the density of a material and the yield strength, so that you could say, okay, here's my minimum requirement for my design. How do I now make it as low mass as possible? So I can, if I'm making a mobile object, just as an example. Now, the same idea is illustrated here, where we try to use some functional performance criteria, but also optimize for an environmental metric, such as the embodied energy requirements. How much energy does it take to actually make the thing? This could also be something like E factor or implicit toxicity. So you say, okay, this is the design metric that I need for my functional performance. What are all of the materials that meet that need? And how can I minimize the environmental impact as I'm making those choices? You can do the same thing for cost. So we can start to build out these databases to help us make the thing that is simultaneously the cheapest, the best for the environment, and still provides a great product to sell to our clients. Now, a notion I want to leave you with is a challenge that I give my students at the end of the term every semester, no matter which class I'm teaching. I ask them to define sustainability for me, and I get some great answers, and I get some really bad ones too, and that's okay. But probably my favorite criteria that a student listed one time was that the global environmental system, as well as our role in it, need to be well understood. We need to understand how our material interfaces to the environment, how our chemistry is going to impact the chemistry of the Earth system. In order to do that, we need to have a deep understanding, and we need to accelerate our methods for understanding those environmental impacts. And if we do that well, we should be able to build better products. Go seicho, arigato gozaimashita.